Introduction to power series. Let's start by defining a power series informally. A power series is a polynomial-like function with infinitely many terms. So let's recall that a Taylor polynomial has a finite number of terms. So here's a generic example of an nth degree Taylor polynomial. Here are all of the terms, and we can see that the last term has x raised to the power of n, so nth degree, and it's a Taylor polynomial because the coefficients are obtained by finding the nth derivative of some function f evaluated at a over n factorial. So again, this has a finite number of terms. A power series would have infinitely many terms. Let's look at a more concrete example. The Taylor polynomial for sine x is given by sine x is approximately x minus x cubed over 3 factorial plus x to the fifth over 5 factorial, and so on, with the nth term being represented by this negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So we say sine is approximately these Taylor polynomials because these would stop at different n values. So here is a graphical understanding where the sine wave is the one that just goes on from negative infinity to infinity. So y equals sine x is the black function. And now let's go ahead and pick one of these. So let's say n equals 5. That's the fifth degree Taylor polynomial. So that is these first three terms right here. That function graphed represents the sine function, but only within a small interval around 0. So outside of that small interval, this fifth degree Taylor polynomial isn't a good approximation anymore. But if we increase the number of terms on the Taylor polynomial, so if we keep going, so let's say we look at a degree 17 Taylor polynomial, that's now represented by this purple curve, which stays closer to the sine function for longer. That interval is longer. And if we increase the degree of the Taylor polynomial, so we can see these higher degrees, degree 29, degree 35, Taylor polynomial, those match the sine function for a wider interval. Well, it turns out that sine x is exactly equal to x minus x cubed over 3 factorial plus x to the fifth over 5 factorial, and so on, as long as it goes on forever. So the main difference here is that we have an infinite series, a polynomial-like function, except that it goes on forever. And so we call this the Taylor series now. So the sine function is no longer approximately, but it is exactly equal to this series that has infinitely many terms. The main idea is that Taylor polynomials only approximate functions near the center x equals a. As opposed to Taylor series, they represent functions exactly. They are the function, mostly, and we will get to that detail soon. Informally, a Taylor series is a Taylor polynomial that keeps going. So the Taylor series for a function f of x centered at x equals a is given by f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial x minus a squared. Here's the nth term. So the nth derivative of f at a over n factorial x minus a to the n. The real difference here is that, again, it goes on forever. So we can write it using summation notation that the infinite series goes on forever, that the coefficients can be found with that nth derivative of f at a over n factorial, and then we have the quantity x minus a to the n. All right, so now let's define a power series. We just defined a Taylor series, but more generically, a power series centered at x equals a is an infinite series of the form, the sum of n equals 0 to infinity, of c sub n times the quantity x minus a to the n. So written in expanded form, we have c sub 0 plus c sub 1 times x minus a to the first plus c sub 2 times x minus a squared, and so on, with the general term looking like c sub n times x minus a to the n, and this goes on forever, so it is an infinite series. And the index can also start at any positive integer. It doesn't have to start at 0. So informally, a power series is an infinite series, but also a function of x, where it converges. So more on that soon. Let's now do a side-by-side comparison. So here is a general power series. We just looked at that. That looked like the sum of n equals 0 to infinity of c sub n times x minus a to the n. Now, a Taylor series is a power series, but C sub n has a very specific formula. To find those coefficients, we use the nth derivative of f at a over n factorial. So the main difference is that a Taylor series is a power series, but there's a formula specifically for finding C sub n. So that's the nth derivative of f at a over n factorial. Now, we can have other special types of power series. We can have what's called a geometric power series, which is a power series with c sub n a constant instead of a function of n. So here, if I have the sum of n equals 0 to infinity of just c, so c isn't changing, it's constant, just c, times the quantity x minus a to the n, this would be a geometric power series. Because to get from one term to the next, we are just multiplying by that quantity x minus a. This quantity is our r value, as we know from having a geometric series, but this is a power series because it's also a function of x, and it's infinite, right? It goes on forever. Here are some examples of power series in summation notation, and we are being asked which are geometric power series. So here I have the sum of n equals 1 to infinity of n squared times x minus 3 all raised to the n. So this is not a geometric power series because what we're looking at is that c sub n in the front. So if that is a function of n, so right here, this is a function of n, it's not just a constant, this would be just a regular power series, not geometric. So no, this is not geometric. Here, the sum of n equals 1 to infinity of 2 to the n over n factorial times the quantity 3x plus 2 to the n. So here, this is also not a geometric power series. If we focus on this piece in front, 2 to the n over n factorial, that's a function of n. It's not just a constant. So also no. This next one, the sum of n equals 1 to infinity of 2 times the quantity x plus 5 to the n, now we have a geometric power series. So if we look at 2 in front, this is just a constant. It's not a function of n. So this, yes, is a geometric power series. And this last one is also geometric. The sum of n equals 1 to infinity of 1/4 times the quantity x minus 4 over 3 to the n. So here, that piece in front is just a constant c. So yes, this is a geometric power series. Where we're headed next is a discussion about when a power series converges. And to understand that idea, we're going to go back and look at or recall the Taylor or Maclaurin polynomial for f of x equals 1 over 1 minus x. So as a reminder, a Maclaurin polynomial is just a Taylor polynomial centered at 0. So for 1 over 1 minus x, that was approximately the Taylor polynomial 1 plus x squared plus x cubed with a general term x to the n. And we want to look at the graphical representation. So 1 over 1 minus x is a polynomial, which is these two pieces here. So I'm going to highlight them. So it's this piece right here, and then there's a vertical asymptote and there's other piece over here. So that's the whole 1 over 1 minus x function. And then here are some Taylor polynomials represented on the same xy plane. So the n equals 1, the first degree Taylor polynomial, would just be 1 plus x to the first. So it's just this line. And this line is the tangent line to the function 1 over 1 minus x. And it's only a good approximation for a small interval around 0. And then the line starts to get further and further away from the curve. If we increase the number of terms, so if we have a 4th degree or a 19th degree or a 30th degree Taylor polynomial, those are a little bit better for longer. So we can see those curves stay closer to 1 over 1 minus x for a while longer, but all of them end up not being so great for certain parts. So 1 over 1 minus x kind of over here off to the left on the left side of -1, not really good. There's none of these higher degree Taylor polynomials are close to that part, and then none of them at all are close to this part over here. So hopefully we can start to see that this Taylor polynomial is only good for an interval of values, a limited interval of values around the center. The center was 0, and it looks like these approximations are only good between -1 and 1 over here. Well, what I just discussed is written here again. So notice that the Taylor polynomials are good approximations near x equals 0, but they start falling apart outside the interval x values between -1 and 1. That's because the sum of n equals 0 to infinity of x to the n is a geometric power series with r equal to x. So I'm going to pause right there. So this expansion is geometric. So notice that to get from one term to the next, we're multiplying by x. So if we multiply by the same value each time to get from term to term, that's the common ratio. So this series, if we consider it going on forever, it's an infinite series that looks geometric in form. So the general form, a r to the n, except that, again, r is equal to x. So in the place of r is x, and a is the first value, which is 1. So what do we know about a geometric series in general? So a geometric series only converges when the absolute value of r, which in this case is x, is less than 1. Well, this absolute value inequality translates to all x values between -1 and 1. So this power series, because it's a function of x, it only converges for certain values between -1 and 1. And graphically, what that aligns with is that the 1 over 1 minus x function is only equal to this power series representation for that set of x values on which the geometric series here converges, or by which the series converges. So it's kind of like the idea of a domain. It's like what x values make this series converge. So when we think about domain, it's like what x values make a function quote unquote work, right? Have an output value. So when it comes to these power series, a power series converges for all x values that make the series converge. To continue wrapping our minds around the idea of a power series converging, we're going to focus on geometric power series. So given a geometric power series of the form the sum of n equals 0 to infinity of c, some constant, times x minus a to the n. So c is a constant, x minus a is the common ratio, is the r value. We can solve the absolute value of x minus a is less than 1. So we're solving when is the common ratio less than 1 to find all values of x for which the series converges. Now we have a special name for that. It's called the interval of convergence. If we want to find the center of the power series, that can be found by solving x minus a is equal to 0. Let's do an example. Let's find the center and all the values of x for which the following geometric power series converges. So we have the sum of n equals 0 to infinity of this constant -2 times the quantity x plus 5 to the n. Let's first find the center by setting this inside part x plus 5 equal to 0. So we can do it in our head, but I'm just going to write it down. X plus 5 is equal to 0. If I subtract the 5, I get -5. So the center is x equals -5. And then to find all the values of x for which the geometric power series converges, what we need to do is recognize that our r value is the quantity x plus 5. And so if we want to solve when is a geometric series convergent, it's when the absolute value of r, so the absolute value of x plus 5, when is that less than 1? So we can take this absolute value inequality, turn it into a three-part inequality. So -1 is less than x plus 5 is less than 1. We can subtract 5 from all three parts, and we have -6 is less than x is less than -4. So this is the set of all x values for which this geometric power series converges. So all the values between -6 and -4. So not including -6, because this is just less than, and not including -4, because again, this is just less than, not equal to. And I want us to notice that what number is just right smack in the middle, or the center of this interval, -5. So we can leave this interval in inequality notation, or if we write it in interval notation, it's all x values in the interval from -6 to -4 with parentheses, because again, we're not including the endpoints. Now we're going to look at some more formal definitions of an interval and radius of convergence. So if we have any power series, the sum of n equals 0 to infinity of c sub n times the quantity x minus a to the n, we are interested in finding the set of all values of x for which this power series converges. This is known as the interval of convergence for the power series. So again, kind of like the idea of a domain. What x values work, as in what x values can I substitute in that will make this series converge? So that's called the interval of convergence for the power series. All power series converge at their center at x equals a, which again we can find by setting that inside part equal to 0. And then the distance from the center to either end point of the interval is called the radius of convergence, denoted by capital R. So in other words, the series converges for all x such that the absolute value of x minus a is less than r. So r is, again, the distance from the center to either end point. So it's like a measure of how wide, how big the interval is. We're going to do another example where we want to find the center, now the radius of convergence, and the interval of convergence for the geometric power series again. So we have the sum of n equals 0 to infinity of the constant 4 times the quantity 2x minus 6 to the n. So let's start with the center. We could set 2x minus 6 equal to 0. So we get 2x equals 6, and dividing both sides by 2, we get a center value of x equals 3. Now we want to try to find the radius of convergence and the interval of convergence. So we want to solve the absolute value of r is less than 1. So 2x minus 6, when is that less than 1? To find the interval of convergence. So we can go ahead and drop the absolute value bars and trap this between -1 and 1. We can absolutely do that, but we also want to find the radius of convergence. And to find the radius of convergence, we want to find x minus a is less than r. So here, I don't quite have that. So the radius of convergence is not 1 because I don't have just 1x. I have 2x here. So what I'm going to do before actually solving this inequality is I'm going to factor the 2 out of here. So I could take out a 2 and I'd have times the quantity x minus 3 is less than 1. And the absolute value of 2 is 2. So I can pull the 2 out of the absolute value bars. and then I have x minus 3 left inside those absolute value bars. And then I can divide by 2. So what I have is absolute value of x minus 3 is less than 1/2. So notice here that I have that center value, right, 3 here. And so since I have like x minus a in absolute values is less than a number, that number is our r. That is our radius of convergence. So r is equal to 1/2. Now I want to go ahead and find the interval of convergence. So I could have solved this original inequality, but that's equal to this inequality. Doesn't really matter. I'm going to go ahead and solve the one down here. X minus 3 is less than 1/2. We're going to go ahead and rewrite this as negative 1/2 is less than just x minus 3 is less than 1/2. And then we'll go ahead and add 3 to all three parts of the inequality. Since I have fractions, I'm going to rewrite 3 as 6 over 2. So we're adding 6 over 2. So we end up with 5 over 2 is less than x is less than 7 over 2. So this is our answer in inequality notation. In interval notation, it's going to be all x values in the interval from 5/2 to 7/2 with open parentheses. And this is the interval of convergence, IOC. Now, just to really understand what's happening with this interval of convergence, I'm going to go ahead and draw just a quick number line here. We know that the center is the x value 3, and the interval of convergence is from 5/2 to 7/2, and that is 1/2 away on each side of 3. So here, 7 over 2, that's 3.5, so that's a half away. And then 5 over 2 is 2.5, or also 1/2, or 0.5 away. So that is the r value, that's the radius of convergence, and this is the interval of convergence. So our interval of convergence is all of the values between 5/2 and 7/2, but not including those endpoints. So one of the main ideas that we have coming out of this is that if we're given a geometric power series, really generically written as this infinite sum of a constant times a linear function raised to the n. So if we have a geometric power series, we can find the radius and the complete interval of convergence. We can find that given a geometric power series. But what is the big picture goal here? We want to determine the radius and interval of convergence for any power series, not just a geometric one. So we want any function of n to be here, any power series, and we want to know what is its radius and interval of convergence. What I want to do next is break this down for you into the three possibilities for the radius of convergence r. So if we have a power series, the radius of convergence could be 0. And that would be the quote unquote bad case, because then the power series only converges at the center. All power series converge at their center, x equals a, but if it only converges at the center, then the radius of convergence would be 0. The next possibility would be if the radius of convergence is infinity, and that is the best case scenario. What's happening is that the series converges for all real x values. So that means it converges for all real numbers. So the radius is infinity because the interval is all real numbers, negative infinity to infinity. But more often than not, in a lot of our examples, it's going to fall somewhere in the middle, that radius of convergence. So the value of r is going to be some number that's bigger than 0 but less than infinity. So some finite number that's not 0. And if that happens, then the series converges for the absolute value of x minus a is less than r. And that turns into this inequality where it's all x values between a minus r and a plus r. And then it's going to diverge outside of this interval. So you might be thinking, oh, okay, so to find the interval of convergence, we just solve this inequality here, and then we'll get this set of solution values here. But that's not the case. We actually have to check what happens at the endpoints. So what happens specifically when the absolute value of x minus a is equal to r? Unless it's a geometric power series. So for geometric power series, we can find the complete interval of convergence. We don't need to check the endpoints because we know on a geometric power series that at that r value, the power series will diverge. But for any other generic power series, we have to check the endpoints. So the interval of convergence for any power series could take any of the following forms. So we could have open endpoints, so we could not include both endpoints. We could not include the left side and include the right side. We could include the left side and not the right side, or both endpoints could be included. We don't know unless we check. And to check for convergence or divergence of a infinite series, we're going to need to know all of the different tests for series convergence. Now we're going to look at a really generic example here of a power series, the sum n equals 0 to infinity, of some c sub n, we're actually not given that function of n here, times the quantity x minus 2 to the n. And we're told that this power series converges for x equals 5 and diverges for x equals -4. So with just those pieces of information, we are now being asked to state whether the series converges, diverges, or cannot be determined for each of the following x values. So what we're going to do is here is our number line with all values marked between -8 and +9. What I want to do is recognize that the power series up here has the quantity x minus 2 inside raised to the n. So our value of the center can be found by setting this equal to 0. So if I set x minus 2 equal to 0, our center is going to be +2. So I'm going to label that value here on my number line. And then our first piece of information is that the power series converges at x equals 5. So I'm going to label that CON for converges. All right, one of the main things that we want to recognize is that our interval of convergence is symmetric about the center. So our interval of convergence, or our radius of convergence, extends from the center, the same number of units to the right and the same number of units to the left. So we know that my power series is definitely going to converge for all values from the center up until 5. So it's going to converge for 3 and 4. So what I'm going to do is just sort of highlight from the center to the right. So all of the values from 2 to 5, including 5, I'm going to converge. And because of the symmetry, I'm also going to converge 3 units to the left, except I don't know exactly what is going to happen at that far left value of -1. Because one possibility for the interval of convergence is from -1 to 5 closed. So open around -1 and closed around 5. So remember that we don't know what happens at the endpoints necessarily. We are told that we converge at x equals 5, and then that's 3 units away from the center. So we know 3 units in the opposite direction all the way up until -1, it's going to converge, but we don't know what's happening at -1. So the smallest possible interval of convergence is this right here, from -1 to 5. So we know that it's going to converge for all values from -1 up until 5, except maybe not at -1. We're not sure what's going to happen there. So I'm going to take this inside part to be all values where I converge. So now let's use that other piece of information. I know that it diverges when x is equal to -4. So now I'm going to go ahead and come over here to -4 and put div, diverges. If our power series diverges at -4, then it also has to diverge at every value less than -4. All right, so now we know what's happening over here at -4 and to the left of -4, and then let's use some symmetry from the center again. So -4 is 6 units away from +2, so let's figure out 6 units away on the other side. That's going to bring us to 8. And we don't know what is happening at 8, much like we didn't know what was happening on the other side of 3 units away from 2 on the left. We didn't know what was happening there either. So we don't know what's happening 6 units away from 2 on the right side either. So in other words, our interval of convergence could be, well, we know it doesn't include -4, but it could go all the way up to 8 and include 8. So this is the biggest possible interval of convergence. I know for sure it diverges at -4, but on the other side, using symmetry, the radius of convergence could be 6, but I don't know what happens at the other endpoint. But outside of that, so anything bigger than 8, I know has to diverge. So I'm going to go ahead and highlight that part red over here. So all of those values have to diverge. Now, anything that we didn't highlight, those places are currently also question marks. Those are cannot be determined with the information that is given. So here we said at -1, we don't know. And then also any value between -4 and -1. We know what's happening at -4, but anything in between there, we don't know. We knew what was happening at 5, but anything bigger than 5, and then all the way up until 8, including 8, we don't know. So those portions there are also question mark portions. And so anything blue in the center here, these are all converging. And then anything red, those are all places where we diverge. So this example is trying to help us understand that idea of the symmetry from the center, the idea that the interval has to be symmetric about the center, the idea of the radius of convergence extending on that same distance to the endpoints on both sides. So that being said, we basically figured out what happens at each of these x values. So over here at -8, we'll go ahead and say that obviously diverges. At -6, that diverges. At -2, -2 is in that gray area, so that is cannot be determined. We can go ahead and label that as cannot be determined. So I can put CBD, cannot be determined. At -1, we said that was that other question mark location too, that cannot be determined. At 0, 0 fell in that interval of converging. So I actually already have that written above. 2 is the center. Absolutely, every power series converges at its center. 5, well, that was given. It converges at 5. That's labeled. 7 falls in that gray area, so cannot be determined. And then 8, we don't know. That one also cannot be determined. But 9 diverges. Looking ahead, how do we find the radius and complete interval of convergence for a non-geometric power series? Well, first, we're going to apply what's called the ratio or the root test to find the radius of convergence R. And if R is equal to 0, the interval of convergence is just the center. If R is equal to infinity, the interval of convergence is all real numbers, -infinity to infinity. But if R is not 0 and R is not infinity, then we're going to find the complete interval of convergence by determining the convergence or divergence of the series at each endpoint of the interval. So in the case where R is just some positive number between -infinity and infinity, we're going to get an interval that we have to check the endpoints on.